Students, this video is for the 6th unit, the 3rd lesson. We're going to be talking about the SAS postulate. In other words, a postulate or a method that allows us to prove that two triangles are congruent. SAS, as you could probably understand by looking at yesterday's postulate, the S's stand for sides, whereas this A stands for an angle. And notice that the angle, this A, is between the two sides. So that's going to be a little hint as to what the diagram has to look like in order for us to use the SAS postulate. Let's take a look at the learning target for today. Our learning target looks like this. We're going to be able to explain the reasoning behind the SAS method. Keep in mind that SAS does stand for side, angle, side, and prove that the triangles are congruent using the SAS method. So that prove does indicate that we are going to be doing proofs, statements and reasons, charts, and everything. All right. In the do now, it asks whether the triangles are congruent. We're supposed to justify our answer for each. And this first one might look a little familiar to you. The second one probably doesn't. So take a few minutes, pause the video, try this one out, and then come back to see if you get it right. First pair of triangles, we can say, yes, these triangles are congruent using the SSS postulate. It's a postulate that we learned about yesterday. We know that AB is congruent to QR. In other words, AB has that one hash mark, and we know that QR also has that one hash mark. It doesn't tell us exactly how long QR is or exactly how long AB is, but it does tell us that those two sides are congruent or have the same measure. Next, we have AC is congruent to PQ, and the reason we know that AC and PQ are congruent is because they have the same number of hash marks, 2 hash marks respectively. And then last but not least, we know that BC, which is this line segment here, it has 3 hash marks, and PR also has 3 hash marks, so that means it is congruent to BC. Again, we don't know their measures, but we know they're congruent. In letter B, for the do now, we have this 2 hash marks here, 2 hash marks here, and we have 1 hash mark here, 1 hash mark here, but then we have an angle that's in between them. So instead of using the SSS postulate, which is side, 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 this doesn't look like that side, side, side postulate. It looks like something else. Around the triangle, we can see the labeling starting from any old vertex here. We go along the triangle and we see first we come up to a side, then we come up to an angle, and then we come up to the side. So we went from side to angle to side. Similar in this triangle, starting at any vertex, we can go hitting one side, and then one angle, and then one side. So this isn't going to be the SSS postulate. As a matter of fact, it's a new postulate that we're going to introduce called the SAS postulate. Remember that using these postulates like the SSS postulate and now the SAS postulate, the reason we're going to use those postulates is to prove that two triangles are congruent using a limited amount of information. Normally, we'd have to say, in order to say that two triangles are congruent, we'd have to say that every single piece is congruent to every single piece, or every corresponding part is equal to every single corresponding part. But when we're using the postulates, they're more like shortcuts. More like if only you can prove these 3 things, then the triangles will be congruent. Let's take a look at a piece of vocabulary that you're going to need for today, which is the word included. And now, just like in many cases in geometry, the word included means something in English, but it means something else in geometry. In this case, and in all of geometry, that word included has a very specific definition. Included means a side or an angle that is between two given parts of a geometric diagram. So between is the operative word here. Included means between. So if they give you 2 parts of a geometric diagram, for example, if they give you 2 angles, let's talk about this diagram here. If they give you 2 sides, if they give you this side and they give you this side, we call this angle the included angle because it is literally between those 2 sides. It's where the 2 sides meet. Over here, we call this a non-included angle. It's not included because it's not between these 2 sides. It's not where those 2 sides join up. We call this side the included side. We're calling it an included side because it's between these 2 given angles, this angle here and this angle here. See how the side is in between those 2 angles? However, we call this side a non-included side. And we're calling it a non-included side because it is not between the 2 angles that are given to us, right? So included means between 2 given parts. Let's take a look at the SAS postulate in terms of a graph. I'm going to try to prove to you that the SAS postulate is the case. So you can see this red, blue, and green sets of sides here. On all three graphs, there are two sides drawn, and the included angle is 90 degrees. You can tell it's 90 degrees because this side is straight up and down, it's vertical. This side is horizontal. Same thing here, a horizontal and a vertical side. Same thing here, a horizontal and a vertical side. So they meet at right angles. Great. If we connect the two ends of the sides to make a triangle, what do you think we'd observe about the connected sides? Try to think this out, pause the video and think about this for a moment, and then come back to see what we come up with. I've drawn in all three sides in purple, and I want you to see something interesting. From here to here, from here to here, and from here to here, in all of these cases, we're going either down or over by 4, and then down or over by 3. So this is 4 and 3. This is 3 and 4. This is 3 and 4. Guess what, folks? These purple lines are all the same measurement. These purple lines have the same exact measurement, and it's going to be 5 units. This leads us to an interesting conclusion. I know that regardless of any other things that are going on with the triangles, if I know that there are two sides that are the same between two triangles, and the included angle, like this 90-degree angle here, that's between the two sides, and the included angle is also equal, then we can say the two triangles are going to be congruent. All of these triangles are the exact same triangle, just rotated or flipped around a little bit. So here's our conclusion. The conclusion is this. If we know that two sides are congruent and the included angle is congruent, then the two triangles must be congruent. So we're able to prove two triangles are congruent using two sides and the angle between them. If I wanted to spell that out using letters, the two sides and the angle between them, SAS. Fantastic. Now that we know that information, let's take a look at what the SAS postulate definition is. The definition says if two sides and the included angle of one triangle, so two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then these two triangles must be congruent. Again, SAS postulate is another shortcut to prove that two triangles are congruent. Let's take a look at the next page for the model problems. Problem, it asks, do the two triangles, triangle ABC and triangle DEF, fit the SAS postulate? Why or why not? Let's take a look at the triangles and the information that's given within them. We can see that there is one side in common. They both have that one hash mark. And there's another side that's in common here. These have the two hash marks. Okay, so far so good. We have the S and the S. Now remember that SAS postulate requires the angle to be the included angle. In other words, the angle that is between the two. So in this case, the angle that is given to us is between the two sides, right? Side, angle, side. If we go along this triangle, we go side first, and then an angle, and then a side. However, in this case, it's not the correct angle. Why not? Because we're looking for an angle that is the included angle between the two sides. We don't know anything about that angle, though. They give us an angle that's out here. So we cannot use the SAS postulate for this problem because we don't have the included angle for both triangles. All right, hopefully that makes sense. Let's take a look at question number 2. What two sides, if congruent, would allow us to use the SAS postulate to prove these two triangles are congruent? The easiest way to do a problem like this, when it's asking essentially which side is missing, is to start from the vertex of the triangle, trace along, and then try to find where the second side should be. So starting from any old vertex, I'll start from point A. I'm going to trace along until I get to a side and then an angle. It should make sense to you that if we have side and then angle, the side that's next should be the side we're looking for. So we already have AC. We already have angles ACB. Now we need side BC. Gives us our side, angle, side pattern. All right, looking at triangle KLM, let's do the same thing. We'll start at one of the vertices and try to trace along to see where the other side is supposed to be. We'll start from vertex L. Going from L to M, we see a side and then an angle. The side that has to follow is side KM. So in order to get our pattern of side, angle, side. So we'll mark that as 2 hash marks. Let's answer the question. Which two sides, or what two sides, if congruent, would allow us to use the SAS postulate to prove that these two triangles are congruent? Well, it looks like it's side BC and side KM. And we write it out like this: BC is congruent to KM. All right, moving on to the check for understanding. This is something that you're going to be doing in class, so I'm not going to go over it. It's just asking you to draw an example of SAS postulate triangles and non-SAS postulate triangles. All right, moving on to model problem number 3. I know that in the learning target, it did say that we were going to be writing a proof, and this is an example of the type of proof that you would have to write. You're given the following information. GH is parallel to PR, those two lines mean parallel. M is a midpoint of GR, and HG is congruent to PR. Using this information, can you prove that triangle GHM is congruent to triangle RPM? Your first step in doing any question like this, a proof question, is to take the information that's given to you and label the diagram. First, we're looking at GH is parallel to PR. So let's put, now careful, this doesn't say congruent, this says parallel. So GH is parallel to PR. In other words, they have the same slope, they run alongside each other and never intersect, and they have all of the relationships that parallel lines and transversals have. For example, alternate interior, alternate exterior, corresponding, that kind of thing. We also know that M is a midpoint of GR. M is a midpoint of GR, which means this point M splits GR in half. Now it doesn't say M is a midpoint of HP, but it says it's a midpoint of GR. So from G to R, that's split up into 2 equal pieces. So GM is congruent to MR. And last but not least, it says that HG is congruent to PR. Now we're told that HG is congruent to PR. So we can say HG, which is this side here, is the same measurement as PR. Beautiful. Just looking at the diagram here, I can see that I have a side and a side, and they meet each other at one vertex, in this case, vertex G. And we also have a given side and a given side. They meet at a vertex, which is vertex R. So if we can say that this angle is congruent to this angle, we're made in the shade. We've got this. And there's one way that we can use to prove that those two angles are congruent. And that method is alternate interior angles. Take a look at these two lines for a second. This is line GH, and this is line PR. I know that these are two parallel lines because it tells us that they're parallel lines. In that case, that means this line here that I'm drawing in is a transversal. If that's the case, that means that the two angles on the interior of the parallel lines that are on opposite sides of the transversal must be congruent. Of course, I'm talking about this angle HGM and this angle PRM. Those two angles are going to be congruent because of alternate exterior angles. Now that we have all of this information assembled, we can definitely prove that triangle GHM is congruent to triangle RPM, and our planning process says that we have a side, an angle, and a side. In other words, two sides and the angle that's in between them. Let's take a look at what the proof looks like. Creating a proof, you should remember to make that T-chart, the statements and reasons chart. And of course, the first statement that you're going to have is the first 3 or 4 or however many things are given to you. So we're going to put all these in the first statement. And the reason for that will be given. They don't have to be in any particular order. We just put them all into that first statement with commas between them. GH is parallel to PR, M is the midpoint of GR, and HG is congruent to PR. And those are given pieces of information. Next, we're going to try to figure out something else about the picture based on this. For example, M is the midpoint of GR. Since M is the midpoint of GR, that means that GM is congruent to MR. These two pieces are congruent. It's easy to see that on the diagram. All we have to do is write that down as our second statement. When you think about the reason, why is GM congruent to MR? Well, I know that GM and MR are congruent because M is the midpoint of GR. That's what it says. M is the midpoint of GR. So I'm going to write down here definition of midpoint. A definition of midpoint says a midpoint cuts a line segment into 2 equal or congruent pieces. Next, what I need to do is identify the fact that this purple angle HGM and this purple angle MRP are congruent, and I know that they're congruent because, as I said before, of alternate interior angles. That's my next statement. Now, at the end of the problem, just to make sure I've got everything set up correctly, I'll go through the problem and make sure everything is in the proof. So I know that this green side, this purple angle, and this blue side are congruent to this blue side, this purple angle, and this green side. So let's make sure that they're all there. HG is congruent to PR. That is here. So I'll underline that in green. And then GM is congruent to MR. I'll underline that in blue. And then the last thing that I have to check is, do I have HGM and PRM congruent to each other? Yes, that's here. So now I have side, angle, side, right? Side, angle, side is congruent to side, angle, side, which means my next and last statement is going to be two triangles are congruent because of SAS postulate. Again, we're saying that SAS postulate is a shortcut in order to prove that these two triangles are congruent. We could prove that every single part of them is congruent first and then say that they're congruent. SAS is just a shortcut. Moving on to the fourth model problem, I'm going to let you mark up the diagram yourself, and then after you're done reading it over and trying to mark up the diagram and coming up with a strategy, I'll show you what the proof looks like. Here's the diagram all marked up. I know that if QT is a bisector of angle RTS, bisecting an angle means cutting it into two equal pieces. And then TR is congruent to TS. In other words, TR and TS are congruent to each other. In order to make this a side angle side, we're going to need this side, this angle, and this side, which is side QT. Oh, how cute, QT. Well, I know that QT is congruent to itself, and that's a property that we learned about earlier in the year. That's called that reflexive property. And we know reflexive property is based on the fact that you can draw an X on this line. So this line is congruent to itself. All right, here's how the statements and reasons look. First, we're going to write down both of the given statements and say that they're given. And we'll write down that these two angles are congruent to each other because the word bisector means it cuts into two congruent pieces. So we say definition of bisector. We'll write down that QT is congruent to itself. Anytime we say any structure in a diagram is congruent to itself, that is the reflexive property. And last but not least, we'll write down that TRQ is congruent to TSQ because of SAS postulate. Just to check to make sure, we have RT, which is a side, we have RTQ, which is an angle, and then we have QT, which is a side, and similarly, we have side, angle, side for this triangle as well. Boom. All right. I would go on and keep going further, but the next problems are in the problem set. You're going to be doing that during class. So we are done with this lesson. This lesson was Unit 6, Lesson 3, the SAS postulate, another shortcut in order to prove that two triangles are congruent. Good luck studying.